So now let's look at some energy release questions with alpha decay. So one thing we have to look at is there's going to be a mass defect here. So my parent and my daughter plus my alpha particle will not be the same. And that little bit of energy that we add to my daughter's side is going to be my change in energy, which is going to be the energy given off. So in other words, we could rewrite this as my change in mass is equal to my parent minus my daughter, or my products. And in this case here, we could either then find my mass change, my mass defect, and then multiply and then convert it into kilograms and multiply it by the speed of light squared, or I could just multiply my total mass defect by 931 mega electron volts per unit. And I'm going to do the second way when we just multiply it. So let's start off here. We have radium-226 undergoes alpha decay. And I want to know what is the kinetic energy of the alpha particle emitted. So first I have to go my parents, which is the mass, radium-226. And then we want to subtract mass of radon-222. And then we want to add the mass of my alpha particle. Now to find these masses, go to, I believe it's page 881 in your textbook, and there's a table there to find these masses to a specific amount of decimal places. On your exams, you'll be either given a table with all of these decimal places, or the question will have the masses for you. So now let's continue this here. So I know my mass of radium-226 is going to be the same as 226.025410 atomic mass units. And then we want to subtract my radon-222, which is going to give me 222.017, that's 570. And my mass of my alpha is going to be 4.02603. Now once I calculate this, I'm going to get 0.005229 atomic mass units. Now what I'm going to do is just multiply by this number here, and my units will nicely cancel off, and I'll get my mega electron volts for the amount of energy given off to the alpha particle. And that's going to end up giving me a total of, we're going to have 4.871 mega electron volts. Now, I want you to try these three questions here. Here are the solutions to those three questions. So now let's look at beta decay. If we remember, there are two types of beta decay. There's one where a positive particle is released, or a positron, and then there's one where we have a negative particle released, or an electron. So we have positive beta decay and negative beta decay. In positive beta decay, a proton is changing into a neutron, and in negative beta decay, a neutron is changing to a proton. So let's first look at the positive beta decay, where a positron is released. So whenever we do beta decay, we always must add in this little neutrino there. It really doesn't affect the balancing at all. You just have to remember to include it. We don't really get into why the neutrino is there in this class, but just remember to include it for beta decay. Now, one other thing we have to look at for beta decay is we are losing a positron. And now when the positron leaves, that's going to leave my charges unbalanced. So let's take a look here. We're essentially a proton's turning into a neutron. So I'm going to end up with 13, and we're going to have 6, and that's going to turn into carbon. So it's carbon 13. Now, right here, if I just take away one positron for the beta decay, what ends up happening is I still have one excess electron. So my charge originally is going to be different than my charge at the end. Why is that? That's because my charge of the nitrogen is neutral. We have 7 protons and 7 electrons. My charge of my carbon is not neutral. We now have 7 electrons and 6 protons, as a proton shifted into an electron. So to make up for that, when we're looking up the mass of carbon, it's going to only give us the mass of actually an atom, not an ion. So in that case, we also have, if we remember, we have a positron being emitted, but we also have to add another electron to my calculations to balance it out, to make sure we have the right mass when we're talking about carbon 6. So there is going to be an electron in the outer shell. And since they're antimatter of each other, their masses are going to be the same. And then we're going to plus my neutrino. So here it says calculate the energy released if the atomic masses are, in this case it's nicely given, 13.05739 for nitrogen and 13.003355 for carbon-13. So we have to first find my mass defect. So my change in mass is equal to the mass of my parent minus my mass of my products. So the mass of my parent in this case is 13.005739. Now my products, we have my daughter, which is carbon-13, which is 13.00355. And we also have two, you might say electrons, because it's a positron and an electron being released. And the atomic mass of a positron or electron, if you look up in that table on page 881, is going to be 0.000549. Now, if we calculate these and put these all together, we're going to end up getting 0.001286 as my mass defect. So once again, we have to multiply this to figure out my energy, the energy release. We have to multiply this by 931 mega electron volts. My atomic units cancel out, and that's going to end up giving me a total of 1.198 mega electron volts. So now let's look at negative beta decay. So if you remember, negative beta decay is when a neutron releases an electron to turn into a proton. So negative beta decay happens when we have too many neutrons and not enough protons for the atom to be stable. So it's going to convert neutrons to protons to get that ratio just right. So let's look at an example of beta decay. So in this example, we're looking at thorium. And what's happening here is thorium has too many neutrons and not enough protons. So a neutron is going to emit an electron to become a proton. So thorium is going to gain one proton, which then makes it protactinium. So it's going to be protactinium 234. Now we're going to also add here an electron and then a neutrino. So now if we add these all up, I have, if we subtract 1, we have the same amount of atomic numbers. We have the same amount of atomic mass. Now, let's try and find here what is going to be the energy of this. So remember, we must find our mass defect in order to solve for the energy released in this electron being released, or the electron being emitted from the radioactive decay of thorium-234 when it goes through beta decay. So once again, mass defect is my mass of parent subtract my mass of my products. But now there's something interesting here with my mass of my products. In this case, I only need to use my daughter. I don't need to use the electron. Now there's a little trick when we're solving the mass defect for beta negative decay, just like there was a little trick when we're solving mass defect for beta positive decay. So for beta negative decay, we actually do not need to use the calculation of an electron. This we could ignore. Now why is that, you might ask? Well, if we think about it, whenever we're looking up these masses, so if we're looking up the mass of protactinium, what we're looking up is the atom, not the ion. So if we remember, a neutron from thorium converted into a proton. Now, and then it releases an electron. Well, this released electron, we have to is kind of like included in this protactinium because it is an atom, not an ion. Do we kind of get that? So the protactinium we're measuring is an atom, not an ion, which means the mass of this is taking into account 91 electrons. Now thorium only had 90 electrons. So then we end up releasing an electron to make us have 91 protons, and that's why the mass of this electron here will be included as well. So that's why we could kind of ignore this mass of this electron, because it is already included when we look up the mass of the atom of protactinium. So then, if I look on page 881, I could find the masses of thorium and protactinium to be, or protactinium 234 and thorium 234 to be these following atomic masses. Now, what I want to do is I subtract them and I end up getting 0.000239 as my atomic mass, or the mass defect. So now, it wants to know what is the energy released. So if we remember, I have to multiply this by 931.5 mega electron volts. And this will allow for my atomic mass units to cancel off, and it'll end up giving me a total of 0.2729 mega electron volts. Now lastly, we just have to go over gamma decay. Gamma decay actually does not change the atomic number since it has a 0 here for my atomic mass, and there's 0 charges. So it doesn't change the atomic number or atomic mass. Gamma decays can be written using just this general form up here. Often alpha and beta decay leaves the daughter nucleus in a highly excited state. So this is where gamma decay happens. After this highly excited state, the nucleus then makes a transition to its ground state and emits a gamma ray. So that's where we get our gamma radiation, which tends to be the most penetrative of all the radiations that we learned earlier.